Well, I think it's about official. Welcome back, everyone. So we're on week 13, I think. I'll have to double check that out of 16 weeks. And this is our special third exam week. Today, we'll take questions from the class on anything you'd like to talk about to review for the third exam. If we run out of questions, that's okay. We do have material down here we could get back into. But I'm not opposed to taking the entire day to review for questions. If there's lots of questions, then that's time well spent, in my opinion. So our third exam is going to start from section 3.4, product rule, quotient rule. 3.5, I believe, is the chain rule. 3.6 is dealing with exponential functions, exponential growth and decay. 3.7 is differentiating logarithmic functions, which means it deals with properties of logarithms as well. And 4.1 was just maximum minimum values and the closed interval method. Well, I'll turn it over to the class at this point. Welcome back, everyone. Where would you all like to start today?
I mean, this might be a bit of a dumb question, but I was just wondering if on the exam it's going to be kind of sectioned like this, or if it's just going to be like differentiate, and then we have to figure out what method we're supposed to be using.
Kind of the latter of what you've said. It's going to be more assorted different functions, and you'll have to decide what is the right method to differentiate each one of those functions. So yeah, like you mentioned, it's not going to necessarily say use the quotient rule or use the product rule. We'll have to determine that on our own. And I think that's an excellent question too. Thanks for asking that one. Other questions at the moment? No worries if you need to take a few moments to think about what we want to go over.
Can we go over number 27 on
Absolutely.
the first example sheet?
Yeah, I'd be very happy to. Thanks for asking that, Alejandra. So 27 on this one, version one. And whatever problems we solve today, I'm going to put a new file right here called exam 3 review questions. So this blank document right here. So first, let's fish out that problem. This one right here, 27, I think I already kind of forgot.
Yes.
Awesome, thank you. So 27, let's just paste it in. And this will be our first question for the day. Thanks for taking the lead on this, on the question to go after. So we want the slope of the tangent line. That's kind of an interesting question because it's not even asking for the tangent line equation. All we want is the slope. So this is a good problem where if we fixate on this instruction, we can actually save a lot of steps. So first off, we have to differentiate the function. That's where we run into a product rule setup. So we have x cubed e to the x. In the product rule, we differentiate our x cubed first. So that'll be a 3x squared. Copy the e to the x. Plus in the product rule, and now next copy x cubed. And finally, differentiate e to the x. There it is. That's the derivative of e to the x. Kind of nice in a way. This is the result. And if we want the slope of the graph at the point 1e, it just means we now need to throw this value 1 inside the derivative. So we'll say next, once I come up with the color here, there we go. M for the slope is going to be equal to, kind of having a change of heart on that. Let me just go this way. Use x equals 1. I think that's a good way to say it. We throw x equals 1 inside the first derivative we calculated. So it'll turn into 3x squared e to the x plus x cubed e to the x. And inside all of those blanks, we're just throwing in a 1. So we've got our slope. We just need to simplify this down. We have 3 times e, and then just 1 times e, for a slope of 4e. And then the problem would just stop right at that stage. Well, any questions, folks, on running through number 27? Absolutely. So Jamie's asking if we factor out our e to the x, our next step would have been e to the x, leaving behind 3x² plus x cubed. Might have been a little bit easier on the next step once we go to put in the slope here, because when it's factored, you're just going to have 3 plus a 1 times e. So it's more immediately giving you the 4e, taking that extra step there. Other questions with this one, or other questions to take a look at? Yes, absolutely. So in the chat, we're going to take a look at 35. I'm assuming the same document, but if folks want to look at the questions out of the textbook, version 2, I'm happy to do that as well. Just take me a moment to open up the textbook. This is a little bit more immediate though, so let's go to 35 here. Looks like we've got, oh, it's way down. There we go. So y is equal to x² natural log 2x, and we want second derivative on that thing. There's multiple different approaches with this one. We can just take the function as it stands and just differentiate it twice. But sometimes with properties of logarithms, anything a little bit extra you do to simplify this could be well worth our effort. So we could say that natural log 2x is the same as natural log of 2 plus the natural log of x. So if we use that information there, we could rewrite y as x² natural log 2x becomes x². Use the properties of logarithms here where we wrote in the margin, and now it's a natural log 2 plus natural log x. Then last step, we have natural log 2 times x² plus x² natural log x. Getting to the second derivative is still going to cause difficulty right here, but the derivative on this spot is not going to be so bad. So that's how I probably start off this one. At least that's how I've done it so far today. Not too sure how we did on the solutions. Next thing we're going to do is a product rule assessment on this portion. But I think the derivative right here is actually pretty tricky. So let's just do a really small example. Let's suppose f of x equals natural log 2 x². Now let's think about f prime of x. Any volunteers from the class on what the derivative should be of this? From the chat, we've got 1/x² times 2. Let's see. Not quite on this one. This one is a little bit trickier to see. So what makes this one a little bit more trickier is that natural log 2 is a huge nuisance. We had a slightly different function, say like g of x equals kx². It's still an arbitrary constant right here, but it's a little bit more concrete. Differentiating this function will give us g prime of x equals 2kx. So that's how this one will go, and it's all because this k right here is a constant. Oh, I ran out of space to actually write down constant. Let me try that again. So since this k right here is constant, when we went to differentiate, it's like differentiating a 3x². 3 stays where it is, the power 2 comes down. But that's the same issue right here in natural log 2. It's honestly not a bad idea to just grab a calculator sometimes if you're not sure about this thing, throw it in. It's a 0.693, so think of that as 0.693 when you go to differentiate. 0.693 doesn't go away, it get doubled by that power 2. So f prime of x would become 2 natural log 2 x. But let me pause right here. Does that make sense to folks on getting that derivative? I honestly find it kind of tricky. Awesome, I'm glad to hear that. Okay, so now that we use properties of logarithms to break this up, we didn't have to, but it could save a little bit of time. We can now differentiate this pretty decently. Could you put it as a 1.386x? Really, we shouldn't because we're going for exact values here. Unless the problem said to round to a few decimal places, we would have to put in 2 natural log 2, unfortunately. So on our next steps, let me get rid of some of this highlighting. Here's what the work is going to look like. On y prime, we're doing the first derivative. We come over here and differentiate. 2 comes down, multiplies the natural log of 2, and now we have just x power 1. And when we go to differentiate that again, x will just vanish and we'd be left with 2 natural log 2. Over here, we're going to use a product rule, so we'll go plus and start off that process. Differentiate x squared for a 2x. Black to say, next we're copying in natural log x, no derivative. Then go plus, x squared copied in. And now finally we differentiate natural log x. That's a nice derivative. It just gives us 1 over x. Before we go and just launch into y double prime, you want to simplify this all as much as possible. So on our next line, y prime is 2 natural log 2x plus, let's see here, 2x natural log x. Nothing really massive simplifies there. Plus, from here we get just an x. So one more step and we'll have y double prime. Any questions so far, folks, to this line?
I have a question. Why is it that it's natural log 2 times x squared, but on the second half of that it's x squared times natural log of x? Why we use the product rule for that second part, but not the first one?
Oh, that's a great question. So the reason this one didn't have a product rule right here is because we're really using, let's just pull it up for really quick reference. We're using this property from section, we're almost there, 3.3. It took me a minute to remember. It feels like that was a while ago already. In this section, we're using this property right here. If you differentiate a constant times a function, the result is constant is unaffected and you're just differentiating the function. So for example, if it's 7x cubed and you go to differentiate, 7 stays in place. We just differentiate our x cubed and we end up with this, a 21x altogether. But another way to think about this one is, you know what? You could have used the product rule right where that orange is. If you use the product rule right here, this is what it would look like. You would first differentiate natural log 2. Then you would go plus, copy in natural log 2. Then you would next differentiate your x squared to get it times 2x. And what would happen next is that derivative goes to 0 because it's differentiating a constant at that line. So it's 0 times x squared plus 2 natural log 2 times x. Oh, let me move this window over just a little bit. And so we get all together 2 natural log 2x if we had used the product rule. But since natural log 2 is constant, this says you really didn't have to. Just move the 2 down and you're all set. What makes this one different is the first factor does depend on x, and so does the second factor. So that means product rule is required on that term here, x squared natural log x. If this looked like this though, that would have been a mistake algebraically, but if this was accurate, we would have needed a product rule right there because now both factors, this one and this one, depend on x. Does that make sense for that question there about the product rule versus what happened here, Emily?
Yes, thank you.
Yep, absolutely. Thanks for that question about that. Other questions so far? Okay, well, it looks like we need to differentiate this line as well. On the very first one, 2 natural log 2 times x, if we differentiate, we just get the constant. 2, natural log 2. So our x just vanishes. On this one, it's a little bit more annoying because once again, it is a product rule. We have something that depends on x, the function 2x, and another thing that depends on x, natural log x. So let's run through just yet another product rule. So let's go carefully. If you're differentiating 2x, you just get a 2 out. And then we copy in the second factor, natural log x. Then go plus 2x copied in. Derivative of natural log x is times 1 over x. And now finally, where the red dot is, we're done with that derivative, the product rule coming in the second time. We move over here, derivative of an x is just a plus 1. So this is what our second derivative turns into. All we need to do is just do some cancellations. So we have gotten 2 natural log 2. We can take this plus 1 if you'd like and just put it with the constants. So natural log 2 plus 1 plus 2 natural log x plus, oh geez, 2. I didn't realize that this was going to cancel, leaving a 2. One more step. We have like terms this time. So it lands at 2 natural log 2 plus 3 plus 2 natural log x. That was definitely a big question. So thanks for asking about this one. This, I think, reviewed loads of stuff for the course. Any questions at all, folks, with this one, or other questions to take a look into? Where did x squared and 1 over x come from? Let me take a look. I'm thinking you're probably on this line here, or maybe, let's see. So x squared 1 over x. So are you referring to, just to double check? Let me use yellow highlighting. This location here? Gotcha. So let me remind myself, seem to have forgotten. Okay, I think I see where it is. So where we got x squared natural log x came from, first we had this portion. When we differentiate that, we got all of this here. But then the next thing we were looking into is, I don't think I want to parenthesis around it. Let's go this way. This portion right here is the product rule. And so all these terms from here all the way over to here is the result of that product rule. So finally, I think I'm ready to answer the question. When we went to differentiate here, we differentiate your x squared. So it comes out as 2x. The stuff highlighted still inside here is the things that we differentiated. The black here means we copied it. So we copied this in the product rule. Then we copied x squared, so that's this portion copied in. And when we went to differentiate this portion in product rule, it turns into the 1 over x. So the answer to the question was pretty much just the output of the product rule gave those last 2 terms there. And just for easy reference, we were using this formula. Fg prime becomes f prime times g plus f times g prime, where that's our f and that's our g. Other questions about that so far? Okay. Well, I'll leave it up to the class. What next direction would you all like to take a look into? Yes, absolutely. So we're looking into 26. Oh, that's the wrong document. Let me go. There we go. This one. And 26 would be, oh, one of these kinds of things. So I think this one came up on a WebAssign. We did it as a lecture problem. So this one could potentially be an exam question. It's kind of a non-standard one though. So I think I'm really glad that we're answering it right here. Let's go up to the second page and What makes this question a little bit weird is it's all about dealing with the product rule, quotient rule, and it looks like constant multiple rule here on part A, but we don't actually even know what the functions f, g, and h are. So this is just emphasizing differentiation formulas more than anything. So let's start off here on part A. It says calculate h prime of 2, where h is defined as these three different versions of functions. So if we're going to calculate h prime of 2, really the first thing we want is the derivative of h in this situation. So h takes on three different forms, but in part A, h prime of x would be equal to, here it's a constant multiple rule. So we will just take 5 times f prime of x minus, here it's another constant multiple rule. So it's a constant 4 times the derivative g prime of x. Once we get that far, we are now ready for h prime at 2. So we're doing this part. H prime of 2 is now going to take and plug 2 here and here. So we'll get 5 f prime of 2 minus 4 g prime of 2. So this is essentially the name of the game. It feels weird because we're used to having the actual function h, but this is all we know about it. It's defined in terms of 2 other unknown functions. But despite that, for f prime of 2, we have a -2 we can plug in. Let me redo that color coding. I want to use blue for the proc roll when it comes up. Let's maybe do it this way. So we'll throw a -2 inside there, and we'll throw, for g prime of 2, a 7 there. So on the next step, we have 5 times -2 minus 4 times 7. This is now turning into -10 minus 28, equaling -38. Unless I messed up my arithmetic, let me double check. Seems okay. Well, any questions, folks, with part A? Okay, on the second part, part B is the more interesting one, in my opinion, because now we're getting into product rule with this one. We might as well say on part A, what we used was constant multiple rule. So now for product rule, we'll organize the functions as we usually do. A first function and a second function, blue and green, or whichever colors you prefer. We just make that window go away. So now for part B, we'll begin by just calculating h prime of x like before. So the way we start is just use the formula for the product rule, which says differentiate f, copy g of x, go plus, and now copy f of x again, but multiply by the derivative of g prime at x. So once we get there, we're ready for the next step, h prime at 2 for this particular function. So it'll become f prime at 2, g at 2, plus f of 2, g prime at 2. So I've done really 2 things. Here, we did the product rule. Here, we took the result of the product rule and just set x equals to 2, so that we could calculate this h prime of 2 indicated above. Any questions at all, folks, to this stage? Okay, I'd say part B is a lot more tricky because now we have 4 different function evaluations. Some of them depend on the derivative, others don't, so we have to really carefully pick out our information. So I'll use purple to signify we're plugging in something for the derivative. So f prime at 2, this whole thing is going to turn into, let's take a look, -2 again. G prime at 2, like before, that's a 7. And let's pick out a different color. But we also need to evaluate g at 2, the original function. All we know is that it comes out as a 4. So a 4 goes in here. F of 2, let's see, that one came out as a -3. So plugging in all that information, we have -2 times 4 plus -3 times 7. So this looks like a -8 minus a 21 for a -29 altogether. So that's how our part B ought to go. We need to do it one more time with the quotient rule. But any questions so far, folks? Okay, let me take this down to the next line. Let's see. Tricky thing about these long problems is finding a level to scroll to. There we go. So we've got our original function, our part C to that function. Below is the information that's supplied on all those functions. So now for part C, major thing about this one is quotient rule, like we indicated. That's organized as the top function versus the bottom function. So when we go to calculate h prime of x, format now for quotient rule goes, essentially this is the numerator, except by the red dot, it's a minus sign. So I'm practically copying what we see here. F prime of x, g of x with a minus. That deserves some kind of highlighting just to emphasize the one change in the numerator. F of x, g prime of x. And then in the quotient rule, we do have a denominator. So the whole thing is divided by g of x squared. So that's the derivative for all x. Now we're going to evaluate h prime of 2 like on the other problems. But that's just a matter of plugging in the information. So first, let's just rewrite this and indicate everything is evaluated at x is 2 now. So f prime of 2, g of 2 minus f of 2, g prime of 2, all of which is divided by g of 2 squared. Scroll down a little bit more. So last thing to do is just come down here, plug in the relevant information. So for f prime at 2, we've got -2 going in. It's multiplying by g of 2, so we're up here finding the information. G of 2 is a 4, multiplying that. Then go minus. In the numerator, we're up to f of 2, which is -3. Then g prime of 2, which is over here, 7. Most of this feels like it's just organization, making sure we're grabbing the right values and not miscopying something. Denominator is g of 2 squared. So we move over to over here. That means it's 4 squared. And from here on out, we're just sorting out the arithmetic. So in the numerator, it's -8 plus 21 divided by 16. So that looks like it's altogether going to be equal to, having a hard time thinking here. There we go, 13/16. That was troubling arithmetic for me for some reason. Well, unless I made some mistake in the arithmetic, that's what that one would come out as. Does that look right to folks so far? Awesome, glad to hear that. Let me get rid of this here so the document just doesn't look weird with that duplicated. So that's this line right here we're about to delete. Unless anyone has any other further questions on this one, I think we're ready for our next volunteer for an example. I'm just going to get some extra white space. Give me a moment. There we go. Oh, we got one from the chat. Dan asks, can we do 44 next? Awesome. I'd be very happy to. So let's go to, oh, that's the solution. So 44. Oh, good call. This is the big punchline to section 4.1, optimizing using closed interval method. So this stands to be a good chance for this method to make it to the third exam. and potentially the final exam as well. Looks like we can fit it on a new page. So it says use the closed interval method to find the absolute maximum, absolute minimum on the given interval. So -2, 1, that closed interval is the given interval they're referring to. And this really is just a sequence of steps. Let's write them out as step 1, find the critical numbers in bracket -2, 1. We might find a bunch of critical numbers, but we only care about the ones inside the domain of the function. So to get critical numbers, we need to differentiate that function. Not my favorite format, so let's also reformat it so it's just more ready to go for differentiation. F of x, not f prime yet, is equal to quantity x squared plus x plus 1 to the 1/2 power. So already in problem 44, this is also a chain rule review problem, so that's awesome. In the chain rule process, we have an inner function and an outer function. There's really two functions here. There's y equals x power 1/2, and there's y equals x squared plus x plus 1. Anyone see which of the two is the inner function? Good call. So the x squared plus x plus 1, that's this function here for the inner function. So knowing that much gets us really pretty much most of the way in setting up the chain rule. So let's call this 2 inner. That means this 1/2 function, that's function 1. Outer, the 1 and 2 are just indicating the order upon which we differentiate through the chain rule. And so here's what it would look like on their next step. F prime of x equals step 1, differentiate this function as if it was that, x to the power 1/2. That would mean 1/2 comes down. The new power is 1 less, so subtract 2 over 2. We now have a power of -1/2. And chain rule says we multiply by the derivative of something. That something is now the inner function, x squared plus x plus 1. It goes here where it's finalized, no change. And it goes here, x squared plus x plus 1, where we do differentiate it. And that's why this says 2, just as a reminder of you differentiate that one second. So on our next step, we've got, let's see, this is a lot of stuff all of a sudden. Probably what I would do to analyze this further is where we have 1/2, let's take the 2 down into the denominator. Because this is to a negative power, we can also drop it to the denominator. The new power would be positive 1/2, or we could use the square root symbol if you prefer. So x squared plus x plus 1 is going down below. This is not something we do the whole lot of in chapter 3, but for chapter 4, it's a good idea to simplify this, make it as pretty as possible, because we have an equation to solve on the top of everything. So far, I just took this whole thing, brought it down together with the 2. We'll multiply this derivative up into the numerator here. So we'll get the 2x plus 1. Because it's not a plus 2 here, that 2 won't cancel. And that's our derivative f prime of x. What we're doing next is solve f prime of x equals to 0. But this is the key step right here, just getting that derivative. Any questions, folks, on f prime of x? Okay, so moving forward to the next step. Solving this whole thing set to 0 just means we're now solving 2x plus 1 equals 0. That looks like a really big leap of logic, but remember, if you set this equal to 0, first step you would take is clear the denominators. So you'd multiply both sides by this denominator. It multiplies against 0, so it's just gone. And the algebraic idea here is the only way a fraction is ever equal to 0 is if the numerator is 0. So that's why we took the extra time to kind of clean this up and not get too overwhelmed with things that didn't matter. So this is an immediate critical number. This implies x equals -1/2 is the critical number of f. Always double check though, -1/2 has to be in this interval. And it is, so that means we're in good shape. We can move on to the next step, step 2. Notice how this one kind of just went from something that looks awful to solve as a function when you set equal to 0 to just a one-step kind of thing. So that can happen on a real exam. Sometimes it looks like a lot of stuff is going on, but just look at the small elements on a step-by-step basis and you'll never lose your way. Any questions at all, folks? Finalizing step 1. Okay, step 2 in the closed interval method is just doing some function evaluations. So we'll write out f of, first we plug in -2. Coming from here, we need to evaluate the function, the original one, so f here, not f prime. We need to evaluate it at the boundary values of the closed set. Then we go and calculate f at -1/2. I regret not putting color coding on that, but it's never too late. So we have to evaluate f at all the critical numbers we found. Then last is f at +1, the right end boundary of our closed set. Because all of these are going inside here, well, f of -2 is going to be square root -2 squared for a 4, -2 here, plus a 1. So this becomes square root of 3. So that's plugging -2 here in the original function. Plugging -1/2 looks like it's a little bit more annoying, but we'll get through it. How do you decide to test those boundaries again? Oh, for the closed interval method, step 2, I should have mentioned here, we always, let me use a different color so it'll stand out. So in the closed interval method, we always evaluate f at all critical numbers and at, there's always going to be 2 endpoints. Of the closed set, whatever set they gave. It'll be formatted as A to B. So in our problem, A is -2 and B is a +1. Other questions about that so far? Okay, looks like we're plugging in next -1/2 inside that function. Let's also scroll so we can see what we're doing here. What in the world? Can't show history. I thought I did a screenshot. Let me try again. There it goes. Now it's cooperating. So we're plugging in -1/2 inside here on the next step. Let's treat ourselves to the calculator on this one. So we'll have -1/2 power 2, plugging it there, that's going to be -1/2, then +1. Comes out as 0.75, so we'll get either the exact value 0.75 if you prefer, or square root 0.75, your choice. Or excuse me, square root of 3/2. So after throwing that to the calculator, this becomes square root. Let's go with 3/4. Sorry, I misspoke when I said 3/2. So I either put in square root 0.75, totally okay if you prefer, it's the exact figure as well, or 3/4 if you prefer. And although this is not a trick you can use on an exam setting, I think on this calculator, if you click on that button, it gives you a fraction. Click it again, it gives you a decimal value, if you ever want to convert something that way. So we've got square root of 3, square root of 3/4. Last is f of 1. That one's not so bad. We would have 1 plus 1 plus 1, which means it is square root of 3. That's kind of interesting. We have a tie on the boundary values. plugging in -2 or plugging in a 1 gives us root 3 either way. And that takes us all the way now to step 4. In step 4, excuse me, not step 4 yet, or at all. In step 3, we're just going to state the maximum and the minimum of the original function f. I think we are done with that screenshot there. So, well, it looks like root 3 is larger than square root 3 divided by 4. So we can now say the absolute max is square root of 3. It's obtained two different ways, at -2 or at +1, but we only need to state the maximum once. And we can also say, and the absolute min is square root 3/4. So that satisfies the closed interval method on this one. Any questions at all, folks, with either steps 2 or 3? Or really any step, of course. Okay. Oh, we got a chat. 34, C or E next. Yeah, I'd be happy to. So let's take a look at that one. That sounds like a long list of derivatives potentially. It's 34. So here's C. I think these don't take too much time, so let's go for both of them. And well, this one is a little bit longer, and this is definitely one we should do. Okay, so we'll start off with part C, then we'll step it up a notch and do part E right after. For part E, by the way, let's take a look at the Moodle website for just a moment. So small break. On the Moodle website, by the exam 3 information, there's the exam 3 formula sheet. We've gotten into a habit of posting this ahead of the exam. And on that formula sheet, we have differentiation properties, properties of logarithms, the closed interval method that we just used. But this has a purpose of helping out anytime a logarithm can come up. And it comes up in a lot of different ways. Surely part E is one of those ways it comes up a lot. So let's park that there when we go to solve part E. Starting on this one, square root of natural log x. Now that's a pretty weird function because what's weird about it is there's no way to use properties of logarithms here whatsoever. So you're going to do the standard thing, kind of like we did on this function. We don't necessarily want to differentiate that with a square root sign on it because it muddies the waters on how the chain rule goes. So instead, we just reformat the function g theta to write it as power 1/2 natural log theta altogether. Then in the same format as the last problem, the inner function is this one, natural log theta. The outer function is this right here. And this gets us set up with a chain rule. It's a tricky chain rule because natural logarithm is in it, so let's also be careful with color coding to show how it goes. So let's start this out. The derivative of g at the input theta begins with differentiate our outer power. So far it's still similar to our last example. 1/2 comes down. We subtract 2/2 for -1/2. Then we multiply by the derivative of our inner function. So we always open up 2 blanks whenever we use the chain rule. Inner function goes in both of them. So it lands right here and here. So that's g prime of theta so far. At this stage, we're just copying 1/2 natural log theta power -1/2. You can drop this into the denominator if you like we did on this prior problem up here. But really the only reason we took this and put it down into the denominator here was because we knew we were solving an equation. So we're trying to make it as simplified as possible. If on an exam setting you leave your answer like this, I wouldn't say that's a big deal at all. It's a stylistic choice. Last thing to do is multiply by the derivative of natural log theta, and that just gives us a times 1/theta. So that's where problem C could end. Sometimes people want to take extra steps, making it look a little bit better. So if you took an extra step, you would get full credit with where that red dot is right here. And you could also write it as 1/2 theta square root natural log theta, if you prefer. No extra points for doing that, unfortunately. And if you made a mistake simplifying it, the way it would be graded would be like a slash here and then an emphasis that you were correct here. But any questions, folks, on maneuvering through part C?
I have a question.
Yeah,
So where does the because I understand like the -1/2 is the square root, but what about the 1/2 in front of the natural log?
this one right here.
Yes, is that the 2?
Yeah, that's where this 2 came from right here.
Okay.
One way you could visualize that is this could also be simplified by rewriting 1/2 times, and then on the next step, correct this exponent here. So it's 1/square root natural log theta. Then on the last step, it's times 1/theta. Essentially what happens now is all your denominators multiply together in that way, and we keep a 1 up top.
Okay, thank you.
Yep, absolutely. Thanks for asking about that. Any other questions, folks, on this one? Okay, well, let's try out part E next, the fun one. It's got a whole bunch of stuff going on there. And something like this we mentioned is a potential real exam 3 question. It's usually going to be formatted this way as a real exam 3 question. It'll be part 1. Expand f of x using properties of logs. Let me fix that letter F there. So we definitely don't want to differentiate this as it stands. I would feel really bad if you launched into that because it's just horrendous. It can take a long time to get through, and it's a mixture of chain rule, product rule, quotient rule, and then product rule, chain rules, quotient rules can come up again as you maneuver through it. So instead, we're going to hit it with a whole bunch of properties. I mentioned before we did this in the past. Some people have done this so often that they just write this down as their very first step, what the end answer is going to be. If you're that kind of person, go for it, no worries. For us, we're going to break it down step by step. Step 1 is from right here, we're going to use the quotient rule. So it looks like this to start. Take the natural log of everything in the numerator, 2t plus 1 cubed. Instead of writing square root t, let's write it as t power 1/2. And then in the quotient rule, we go minus. Notice that minus is there in the quotient rule for derivatives as well. So that's kind of a helpful way to remember these things. The natural log of everything in the denominator, e power t, 3t minus 1 to the 4th power. And we're done with property 6 so far. I should write out that this is f of t, just to emphasize what we're working with. It's not the derivative yet, just properties of logarithms. Now, at the next step, we have a product rule. The product rule happens because of here, we're multiplying 2 functions, and right here. So that's property number 5 coming in next. Property number 5 says we break this up by writing natural log 2t plus 1 cubed plus natural log t power 1/2. So that's the product rule used here. There's an extra danger in this problem. That negative sign is a nuisance when the product rule comes up again, because we do have to distribute this through. So a good call is to just start with a negative sign and a parenthesis. Here we use product rule again and get natural log e to the t plus natural log 3t minus 1 to the 4th power. That's a lot of closed parentheses right here. But so far, so good. We're going to need to distribute the negative sign in but we're still needing one more property. Oftentimes in an exam situation, people stop right here, even after distributing the negative sign. That's not a good stopping point because differentiating all this stuff requires 1, 2, 3, 4 different chain rules. And they're not easy chain rules either, because if you look at these, that's 1, 2, 3 different functions in our chain rule. We never really did those problems at all. So we need to do something to break this down even further. Anyone see what the last property is that we can use? Oh, sorry, I just missed that chat. Absolutely, we can cancel the E right here. Let's emphasize it this way. There it is, gone and canceled. Actually, maybe a different color is probably better. There we go. So we have a big cancellation there. Good call. That property is where we just made a cancellation occur. This one right here. The natural log of a base b of an exponential to the same base cancels things out. Natural log is log base e, so it's log base e of e to the power of t. We get just a t out. But there's even one more property. Anyone see what the next to last property is? Good call, Cameron. We can use property 7 now. Property 7 is going to affect this, this, and this. So what happens next is, let me write here, natural log a times b is natural log a plus natural log b, just writing down on as a paper trail what the properties are as we used them. And our last step, natural log of a to a power is that power times natural log a. So just to reemphasize, not taking this last step makes the derivative in part 2 really, really hard. So definitely try to expand it completely and utterly fully. Power 3 comes down. It's natural log of 2t plus 1 plus a half comes down, natural log t. Over here, we're going to distribute the negative sign and get minus t. Here, 4 comes down. The negative sign distributes in, so now it's a minus 4. Natural log 3t minus 1. This is as far as it can fully expand because pluses and minuses inside your logarithm function have no properties that we can use to expand these even further. But that's okay. This is finally a function that's not too bad to differentiate. So that takes us to part 2. Differentiate. The answer in part 1. Before we launch into that derivative, any questions at all, folks, with the properties of logarithms here? Okay, let's launch into it. On the very first one, it's a chain rule, but it's a chain rule of just 2 functions this time because we moved the power 3 down. So we have this as inner and natural log as outer. So let's go calculate the derivative next. F prime of t on the next line is going to be 3 times, when we go to differentiate the natural log, everything that's the input goes down into the denominator, and then we multiply by the derivative of that input. So that's how the chain rule will go. We handle derivative 1 outer, then plug 2t plus 1 in all those placeholders. They'll go here and here. If you want to save a step, if you already knew you're differentiating 2t plus 1, you might have just wrote a 2 right here, and that would have been just fine. So this derivative is done, just need some simplification on our next step. We move on to the next one. Here we're using the constant multiple rule. It's the constant 1/2 multiplying the derivative of natural log t. But that derivative is just a 1 over t, nice as possible. Here, that's another nice derivative. We just get a -1 for that portion. And over here, it's another chain rule. So let's write -4 times, same exact analysis as before. The 3t minus 1 is our inner function. The natural log is our outer. So when we go to differentiate, first, the natural logarithm does this. Throws everything under the bus. Our input is now in the denominator. Next thing we do is we take 3t minus 1, plug it into the last two positions. And we're just about there, folks. We need to calculate two derivatives and just simplify the rest of this stuff we're looking at. Any questions on the first line, getting that derivative? Okay, let's now analyze this then. On this fraction right here, 2t plus 1 stays down below. We can drop parentheses or just to visualize how the chain rule is working. The derivative of this comes out as a 2. It'll multiply the 3 in the numerator into the numerator. So that's our first term, 6 over 2t plus 1. This one we can simplify by writing it as plus 1 over 2t. Just multiply through our denominators and numerators. Then it's a -5. Or hang on, that is really bad of me. That's an order of operations failure right there. Let me just highlight that to emphasize what not to do. I saw the -1, I saw the -4, I subtracted them together, but I failed to see that. That's really important. That means order of operations does not go that way. We need to be more careful. I'll leave that yellow there just to emphasize. This -1, we just copied in and we can't do anything with it. Then it's going to be minus. Now here we have -4. Multiplying this derivative, which is a +3, so it's going to be 12. -12 is already -12 is already part of our answer, is what I'm trying to say, because I put the negative in front of the fraction. If you went like this, plus a -12, that's just a different stylistic way to say the same thing. So we have a -12, denominator is just a 3t minus 1. And this is where the answer stops. We'll never try to find the least common denominator or anything like that. When we get to part 2, this is the stopping point. Well, I think that's the toughest derivative we've done so far today. Any questions, folks, on any of this process?
Yeah, could you explain what happened to the 1/2 times 1 over t again?
Yeah, absolutely. So this part right here, as a 1/2 times 1 over t, because we're doing a multiplication of fractions, the work is just multiplied across the numerators, so it'd just be a 1 times 1, and then multiply across the denominators, so it'd be a 2t. Does that make sense there for that question?
Yeah, no, it does. Then could you maybe explain what happened to the derivative of 2t plus 1 then? I guess I
2t
kind of
plus 1,
lost
yeah.
something in there, yeah.
Yeah, absolutely. Let me take a look at that one. So for the 2t plus 1, when we go to differentiate this, we get a 2 out. And it looks like I took the 3 and the 2 and just multiplied them together to get the 6. They multiplied both back into the numerator.
Okay, yeah, no, that makes sense. I'm caught up. I don't know where I started missing something.
You know, to me personally, I make mistakes on this kind of stuff because for me, there is so much stuff you have to look at once that it becomes kind of overwhelming. So when there's that many things, the best strategy really is to try to imagine you're looking through like some kind of small scope. So you're really just focusing on one element at a time instead of looking at everything at once. I think I missed it. Let me see here. Yeah, I agree with you, Hannah. These longer problems are pretty rough in that kind of sense. So it's a weird comment to make, but with these longer problems, if you go a little bit slower, you're actually going faster because That way you're thinking methodically on every little step and not trying to get overwhelmed with all the extra little details. Well, any other questions, folks? On this one or other ones to take a look at? You know, thinking of the problems that we've done so far today, I think we've run the gamut and done everything except exponential growth and decay. We can make that our next problem. How's that sound to folks? Oh, we've got lots of responses over chat for that one. All right, let's give this a try. So on exponential growth and decay, let's see here. That's got to be section 3.6. Some of these are harder than others. I think a problem like 33 probably does not make it a good exam problem, but it's a good one to take a look at in practice because it's a little bit extra challenging. It'll make the actual exam a little bit easier. Something that's more of a routine exam problem might be something like, say, let's see, maybe something like 32. Let's see, at certain time T0 days, the amount remaining is 20 milligrams. What is the rate of decrease of the sample? I think that'll be a pretty good one. Let's try it out number 32. I said, not too sure on that one because I feel like the one that I really would ask on the exam would be pretty similar to quiz number 6. So take a look at your old quiz 6, how it went. I'm writing down a question that looks a little bit more similar to this. It could be exponential growth or decay, but it'll be more like find the number of cells in 1.2 hours, find the growth rate at 1.2 hours for a type of question. So on this one right here, let's see how it starts. Part A wants the relative decay rate, and we're dealing with a half-life problem, so that's actually pretty helpful for us. Bismuth 210 has a half-life of just 5 days, so that disintegrates really quickly. So lambda itself represents the half-life. And we have a sample of starting mass 800 milligrams. So we can say mass at time 0, 800 milligrams of bismuth 210. And all we want in part A is the relative decay rate, K. But that's actually a pretty fast process. K by formula in this situation is negative natural log 2 divided by your half-life lambda. So this becomes negative natural log 2 divided by 5. So that gives us our relative decay rate. And that's all they were asking for in part A. That means we're already now on part B. Any questions, folks, on getting the decay rate here? Okay, so part B is written in a kind of funny way. It says at a certain time, T0 days, we don't know that value, we have just 20 grams remaining. At this time T0, what is the rate of decrease of the sample? Really, that's kind of a layered question. Let's say for part B, here's step 1. We need to write down what the mass function even is that decays exponentially. It's mass at time t equals initial mass times e to the power kt. In part A, we solved for k. We also wrote down this. I mean, it was just part of the problem, stated right here. So that gives us our value that goes here. So we need mass at t equals 800 e to the power of k, which is at negative natural log 2 divided by 5 times t. So I'll write it in this way. Negative t natural log 2 divided by 5. So I'll just throw t in right there so it doesn't look like a t minus something. And that's our mass function. So it says there's a certain time at which we have 20 milligrams. What is the rate of decrease of the sample at that time? Well, for step 2, looking at this, I'm not too sure we needed step 1, but hey, it's here for just for the sake of the exam review, I guess. Let me rewrite this as for part B, we need to use an equation that goes dm dt, evaluate at a time t, equals t naught, equals k times mass at t naught. Oh, and sorry for missing that chat there. Yes, it is, absolutely. Where the x that you cited in the denominator is always the half-life. It only works in the problems where we have exponential decay going, but this is a legitimate formula that always works right here. Let's write out, just to emphasize that that formula is very helpful. If you left this off, no, you would not lose points for that. Other questions so far? Okay, well, last things to do here is plug in the value for K, plug in the value for mass at T naught, but it said mass at time T naught is 20 milligrams. So I guess this example we're doing right now is mainly to emphasize the derivative portion of the whole problem. On your quiz number 6, that was part C, find the growth rate. So all we now need to do is say that this is equal to K, which is that negative natural log 2/5, multiply it by mass at time T naught, which was stated in the problem to be 20 milligrams. These usually have an information of rounding to a certain decimal place, but if I forget to say that on the real exam, use your best judgment is what I would say. Also, for the sake of partial credit on a real exam, let me write down this comment here. Write on paper what goes in the calculator for, let's say, major partial credit. The philosophy here is it's the calculus that we really are trying to grade on, and it's very easy to just make the tiniest of mistakes when you put that into your calculator, especially if it's more built up than what we see there. So if you get in the habit of always writing down on paper what is about to go in the calculator, even if your number is totally off, I'll look at this and grade it on partial credit here. You might lose like a half a point if everything there is correct. But let's see if we can get the same values. This is a good time to practice with your calculator if you have it pulled out. So go negative natural log 2, divide by 5, multiply that quantity by 20, and we have a decay rate of, let's go to maybe 2 decimal places, negative 2.77. And I forget the quantity. It's in milligrams, I mean the unit rather. Milligrams per day. So we're losing, at whatever time T naught this was, this amount per day. Well, that finalized that problem there. This one was a little bit faster than I expected, but any questions or comments with it? Okay, well, we're now at the weird part of the class where we've got about 5 minutes and a little bit of change. Any other questions that folks would like to take a look at with our remaining time?
Actually, I'm a little confused as so in part B when you skip from 800 times e to the neg and then down below it's k times mtl. Like what happened to the natural log up top?
This stuff right here.
Yeah.
Well, what happens here is, sorry, go ahead.
No, you can go.
Well, what happens with this function right here is when you go to differentiate it, it always comes down as just K times M of T naught. So just to visualize it down below here, we go M of T prime, or dm dt if you prefer, either way you'd like to say it.
Mm-hmm.
Derivative would be 800 copies in.
Yeah.
We multiply by the derivative of that exponential. So it's going to be e to a power, multiplied by the derivative of that power. So this is a chain rule setup. Power going up in here is negative t, natural log 2 fifths. And then that means same quantity also goes down over here. Let me write it down slightly different. Negative natural log 2 divided by 5 times t. So that's what the setup would look like to that stage. Then from over here, we're just copying 800 e to the power of negative t, natural log 2 fifths. Here's where we take a derivative, but this part by the red dot is a constant, multiplying a variable to power 1. So when you differentiate that, you just get negative natural log 2 fifths. But this is the part where it finally gets to where we can answer the question you're referring to. We had the original function right here, but part B was asking about a derivative. So we just skipped down to and wrote down the derivative. But if we differentiate from scratch, right where the red dot is, notice that this part is K. That's the K that's being referred to right here. And
Right.
800 to that power, all of this stuff, that's the mass at T naught.
Okay.
Kind of a bizarre formula, but I guess that's a good takeaway on this, is that this formula
Yeah.
here,
That all
very
rings a
helpful.
bell now.
Awesome, glad to hear that. Thanks for asking about that.
Uh-huh.
Oh, I'm misspelling helpful. That's not helpful at all. Let me try this again. Okay, and I think I missed a chat in the middle of your question as well. Well, it looks like we might not be able to get an exponential decrease to go completely in the limited amount of time we have, unfortunately. Sorry about that. But I could take another really short question. Any volunteers for one last question? Okay, well, this might be a good stopping point for us today. But if you have more questions, exponential growth, decay, or anything otherwise, I'm back on office hours at 3:30. Just gonna take a short break and I'll be right back on Zoom. Well, have a great afternoon, folks. We won't meet on Wednesday because it's the exam, but I'll still be available for questions and office hours on Wednesday. So I'll talk to you all later, and we'll be back to our official class once again in a week's time. Take care, folks.